Now let us perform shell mass balance over delta Z. We know for mass shell balances, rate of mass of A coming in minus rate of mass of A going out plus rate of production of mass A by homogeneous reaction is equals to 0. Now as we are performing for homogeneous reaction, we know this should be 0. So the only term left are rate of mass A in and rate of mass out. So using flux at Z and flux at Z plus delta Z. So mass would be flux into area. So let us assume area to be S through which mass is flowing. So S into N at Z equals to Z minus S into N at Z equals to Z plus delta Z is equals to 0. Now dividing both sides by S into delta Z. So it would be NAZ minus NAZ at Z plus delta Z upon delta Z is equals to 0. Multiplying by minus 1 minus NAZ at Z upon delta Z equals to 0. Now for infinitely small delta Z, that is delta Z equals to 0, by using definition of differentiation, we get minus of dNA Z upon dZ equals to 0. Now we have this equation and equation number 2. Now putting equation number 2 in 3, we get now as we did in heat transfer and in momentum transport, we would do the same on integrating double integration. On first integration we get one constant, that is minus C of dAB upon 1 minus half of xn is equals to C1. Now taking the CA dAB on division, we get Considering is a new constant C1, so we get 1 upon x dx by dz equals to C1. Now on further integrating, we get minus of 2 ln 1 minus half of x is equals to C1z plus C2. Now to make calculations easier, we would change C1 and C2 into other constant such that its value is easier to calculate. So let C1 equals to minus of 2 ln K1 and C2 equals to minus of 2 ln K2, where K1 and K2 are other constants. Now the equation becomes minus 2 ln 1 minus half x equals to minus 2 ln K1 into z minus 2 ln K2. Now using boundary conditions, to get the value of the constants, on first we would use, we know that at x equals to 0, xa equals to xa naught, which is given in the question here, which would give us one constant, and other would be at x equals to del, that is at the boundary of the stagnant film of gas, xa will be 0, which is an logical boundary condition for this condition. Now on solving, we get 1 minus half xa minus 2 of ln of this is equals to minus 2 ln K1 times of z plus minus, putting x equals to 0 and x equals to xa naught, we get and x equals to del, final equation becomes 1 minus half of xa is equals to 1 minus half of xa naught to the power 1 minus z by del. Now we got concentration profile in the gas film. In the gas film, that is concentration XA varying with Z. Now we can put it in equation. Na equals to NZ equals to NSCDAB upon 1 minus X putting this here, we will get NaZ, which is the molar flux of A at Z, is equals to 2 times of C TAB upon del, which is the length of stagnant gas film, into ln of 1 upon 1 minus half of x naught. Now we can say that NaZ is local rate of reaction. Obviously it is flux, so it would be per unit area, but here it would be per unit area of catalytic surface. Now we can use this NaZ to get overall conversion rate in the entire reactor. Although the chemical reactions occur instantaneously, at the surface of the catalyst, but still the conversion of A into B proceeds at finite rate because of the slow diffusion. Hence we can say that conversion is controlled by diffusion between A and B. Now let us see another question for diffusion with heterogeneous reaction. But in this, it is just last question with slow heterogeneous reaction and not instantaneous at the catalyst surface, that is at x equals to Z equals to del. Instead, we would assume that the rate at which A disappears at the catalyst coated surface is proportional to concentration of A in the fluid at the interface. That is NaZ equals to K double dash Ca equals to K double dash Cxa, in which K1 double dash is a rate constant for the pseudo first order surface reaction. So it is given that 2A giving B is not instantaneous and is a slow reaction. Assuming rate to be proportional, we know that NaZ equals to K1 dash Ca is also equals to K1 double dash Cxa. The differential equation from the last question would be same, that is minus of 2 ln of 1 minus half of xa will be equal to 2 ln K1 times Z minus 2 ln K2. Only here boundary condition will change. First boundary condition, which is at x equals to 0, xa equals to xa naught, would be same. Second one, where x equals to del, that is at the boundary of stagnant gas film, xa will not be equals to 0. In fact, it would be equal to Na by K1 double dash C equals to Xa from this equation. Now putting this in the above differential equation, to get the values of constant k1 and k2. We get the final equation as 1 minus half of Xa is equals to minus half Nz, which is a constant, to the power z by del into 1 minus half of Xa naught to the power 1 minus z by del. Now this equation is too complex. Now for concentration profile, let us get the value of dxa by dz at z equals to 0. On differentiating and putting z equals to 0 and Xa equals to Xa naught, we get the value of dxa by dz as minus 2 by del c, no, not there, let's see, minus 2 del ln 1 minus half of Nz divided by k1 double dash c upon 1 minus half Xa naught. Now putting this in equation, Nz equals to minus c dab upon 1 minus half of Xa here. The value of dxa by dz would be this only. Putting this value here, we get Nz is finally equals to 2c dab upon del into ln 1 minus of half Nz k1 double dash upon minus half Xa naught. Now this is the final equation for the concentration profile, and the rate of the combined reaction and diffusion process is given by it.